So here three-phase AC circuits, or otherwise we can call it as the polyphase circuits. Polyphase circuit. Here a three-phase supply is a set of alternating quantities displaced from each other by an angle of 120 degrees. A three-phase voltage is shown in figure. It consists of three phase A and phase B and phase C. This is a phase. A phase waveform starts at 0 degrees. Phase B waveform starts at 120 degrees, and phase C waveform start at 240 degrees. So this is a, so they draw three phase waveforms, and the axis is taken as the degrees and y axis is taken as the magnitude of voltage, that is E. Here they are showing in figure A phase, B phase, C, and how much they displayed phase angle. So each one is 120 degrees. Each one is 120 degrees. So now this waveform, see, observe this one, plus EM minus EM. Plus EM means positive maximum, negative EM means here negative maximum. Here all three phase maximum voltages are same. Magnitudes are same, but they are differs with some displacement angle, some angle. So now here the three phase voltage can be represented by a set of three equations as shown below. Now EA is equal to EM sin omega t. This is for A phase equation, instantaneous equation, and EB is equal to EM sin omega t minus 120 degrees. That is for B phase equation. B phase is displaced by 120 degrees, and the written here in B phase sin omega t minus 120. In C phase, EC is equal to EM sin omega t minus 240. That means here minus 240 means it is displaced by 240 degrees, minus 240 degrees. So in C phase we can write in another way, that is EM sin omega t plus 120 degrees. Here the sum of the three phases voltage at an instant is equal to 0, that is EA plus EB plus is equal to 0. The phasor representation of three phase voltages is shown here. This is the phasor representation. EA, EB and AC. EA and EB and AC. So this is the representation, phasor representation. Now here the phase A voltage is taken as the reference and is drawn along the x-axis. The phase of B voltage, the phase B voltage lags behind the phase A voltage by 120 degrees. Here the phase C voltage lags behind the phase A voltage by 240 degrees and phase B voltage by 120 degrees. Here the generation of three-phase voltages. Three-phase voltage can be generated by placing three rectangular coils displaced in space by 120 degrees in a uniform magnetic field. When these coils rotate with a uniform angular velocity of omega radians per second, a sinusoidal EMF displaced by 120 degrees is induced in the coil. Now here the necessity of and advantages of three-phase system. Here three-phase power has a constant magnitude, whereas single phase power pulsate from 0 to peak value at twice the supply frequency. Here a three-phase system can set up a rotating magnetic field in stationary windings. This is not possible with a single phase supply. So now for the same rating of three-phase machine or smaller, simpler in construction and have better operating characteristics than single phase machines. Next, the transmit the same amount of power over a fixed distance at a given voltage. The three-phase system requires only 3/4 the weight of copper that is required by the single phase system. Here next one is the voltage regulation. The voltage regulation of a three-phase system. The transmission line, three-phase transmission line is better than that of single phase line. Now these are the very important aspects, advantages. So now the phase frequency of these, how can we attain this phase sequence? Here see, observe this one, the order in which the voltage in the three phases reach their maximum value for the waveform. Here see, here in the shown figure, shown figure, the shown figure, so the waveforms are shown here in this case. So if phase A is attaining the phase A is attaining the maximum magnitude, after that P phase is attaining the maximum value, and then after that C is attaining the maximum value. So then we say that the phase sequence is A, B, C. Her order of the phase sequence is A, B, C. So now here we go for the balanced supply. A supply is said to be balanced if all three voltages are equal in magnitude, and displaced by 120 degrees. A three-phase supply can be displaced by 120 degrees, and a three-phase supply can be connected in two ways, either in delta connection or in star connection. So see here, this is the delta connection. EA, EB, EC, these are connected in delta manner. So the terminals are A, B, C, and see the next one is the star connection. Here EA, EB, EC connected a common point, so that is star or delta, that is called a neutral point. The terminals are A, B, C, and you see here balanced load. A load is said to be balanced if the impedances in all three phases are equal in magnitude and phase. Magnitude and phase. Here also the load can be connected in two ways, either in star or delta, or otherwise delta or star. Here see, observe this one, the load is in delta connection. The load is in delta connection. Here ZAB, ZBC, ZCA, and those are the impedance are connected in delta manner, and A, B, C are the terminals. So now see here the star connection. Here ZAB, ZB, ZC, these are all connected a common point called neutral. So the terminals of A, B, C, this is for the load, star and delta connections. Now a balanced star connected load. A balanced star connected load, as shown in figure, a phase voltage is defined as voltage across any phase of the three-phase load. The phase voltage is shown in figure. EA, EB and EC. A line voltage is defined as the voltage between any two lines. The line voltage shown in figure are EAB, EBC, CA. The line currents are IA, IB, IC. Star connected load, the phase currents are same as the line current. See, observe here, was this one. So here between the A terminal and common point terminal, that means the load across the voltage across the load is called phase voltage, that is EA or EB or EC. So now the line voltage between the terminal A and B, that means the line terminals, that across these terminals is called line voltages. Here the current IA is called IB, IC is called the line current. These currents are also called the phase current in this diagram. So now from this diagram, so using Kirchhoff's voltage law, the line voltage can be written in terms as shown below here. The phase voltage as shown in terms of the line voltage in terms of phase voltage as shown below. Here EAB is nothing but it is the voltage between two line terminals. Here, so EA and BB. EAB is nothing but EA minus EB. But EAB is the line voltage, EA is phase voltage, EB is phase voltage. And also here EBC line voltage equal to EB phase voltage minus EC phase voltage. Here ECA is equal to EC phase voltage minus EA phase voltage. That means here EAB is equal to EA minus EB, EBC is equal to EB minus EC, ECA is equal to EC minus EA. The phasor diagram shows the three-phase voltage and the line voltage EAB drawn from EA minus EB. So phasors. The phasor current IA is shown. It is assumed to be the load is inductive. Here in this phasor diagram, EA, EB, EC, these voltages are called phase voltages. Now, so we want line voltage. What is that line voltage? For example, we want EAB. EAB is nothing but what? EA minus EB. EA minus EB. Here EA minus EB is nothing but EA is it is in along x-axis, and E minus EB is the opposite direction of the EB. Minus EB is nothing but it is the opposite direction of the EB. So these two resultants here, EA and minus EB resultants, which gives that EAB. EAB and EB is projected, and then it resultant is EAB. So that is resultant voltage is called EAB, that is line voltage. So see here, EA and EAB's angle is 30 degrees, EB and EAB is 30 degrees. Here between the EA and minus EB is 60 degrees. The resultant line voltage EAB and the IA is here. The phase angle is EAB and IA is phase angle is 30 plus 5 degrees. Phase displacement is 30 plus 5 degrees. So now from the phasor diagram we see that the line voltage EAB leads the phase voltage EA by 30 degrees. So the magnitude of the two voltages can be related as follows. EAB is equal to EA cos 30, that is equal to root 3 EA. Hence, for a balanced star connected load, we can make the following conclusions. EL is equal to root 3 E phase, IL is equal to I phase. Line voltage leads phase voltage by 30 degrees. Here this is the about the line voltage and the phase voltage. Here three phase power. In single phase circuit, power is given by P is equal to VI cos pi. Rest of it can be written as V phase in three phase. It can be written as V phase I phase cos pi for a single phase circuit. So here the power in three phase circuit is 3 times than that of single phase circuits. So now power is equal to 3 into E phase I phase cos pi, and power in three phase in terms of line voltage and line current. So power is equal to root 3 ELIL cos pi. This is about the three phase power. So now the balanced delta connected load. A balanced delta connected load, the phase currents IA here, IAB, IBC, ICA, the line currents IA, IB, IC for a delta connected load, the phase voltages are same as the line voltage. Here say observe this one, EAB, EBC, ECA, and the current IA is divided into IAB, ICA. So IB is IBC. Here see, using Kirchhoff's current law, the currents in the written can be written in the terms of phase currents. IA is equal to IAB minus ICA. IB is equal to IBC minus IAB. So IC is equal to ICA minus IBC. This is the phasor diagram. We can see this one and we can calculate this currents from this phasor diagram. Here the phasor diagram shows the three voltages EAB, EBC and ECA, and three phase currents IAB, IBC and ICA. It is lagging behind the respective phase voltage by an angle pi. This is drawn by assuming that the load is inductive. So from the phase currents IAB minus ICA, the line current is IA is drawn as shown in figure. From the phasor diagram, we see that the line current IA lags behind the phase current AB by 30 degrees. The magnitude of the two currents can be related as follows. IA is equal to IAB cos 30 degrees, that is root 3 IAB. Here, hence, for a balanced delta connected load, we can make the following conclusions. IL is equal to root 3 I phase, EL is equal to E phase. So line currents lags behind the phase current by 30 degrees. Here, the three-phase power for a delta connected load can be derived in the same way, so that as at for star connected load, for P is equal to 3 E phase I phase cos pi. In single phase, for P is equal to V phase I phase cos pi. For three phase, power is equal to 3 into E phase I phase cos pi. In terms of line voltage and line currents, the power is equal to root 3 EL IL cos pi. So here, from this, so observe this one, star and delta once again. Here in the star connection, the line voltage and phase voltages are different. Here the line voltage is equal to EAB minus EA minus EB, that is for line voltage. EBC is equal to EB minus EC. ECA is equal to EC minus EA. Here from the phasor diagram we can calculate the line voltage, that is EAB is equal to root 3 EA. EL is equal to, that means here line voltage is equal to root 3 phase voltage, and here the star connected, the current is same line current and phase current. So we can write in this way, IL is equal to I phase. So now the three phase power in the star connected is, power is equal to 3 E phase I phase cos phi. It is in phase manner. Now we can write in line currents, the power is equal to root 3 ELIL cos phi. Here the delta connected, in delta connected, here the delta connected, the terminals across the A, B, C is So AB terminals is called EAB voltage is called line voltage. This line voltage appears across the load, that is the load voltage is nothing but a phase voltage. Here in this case line voltage and phase voltages both are same in delta connected, but here the currents are different. See, observe this one. There is from IA is equal to IAB minus ICA. Here, see, EAB is taken as a reference, IAB minus ICA, which gives that IA. So, between EAB and IA, the pi and the phase angle is, that means the phase displacement is pi plus 30 degrees. Here, the line current IA is equal to the line current IA is equal to root 3 IAB, that means IL is equal to root 3 I phase, and line voltage is equal to phase voltage. The three phase power in delta connected can be written as power is equal to 3 into E phase I phase cos phi, and then in terms of lines power is equal to root 3 ELIL cos phi. So, this is about the star and delta line voltage, line current, phase voltage and phase currents.